Hey, how's everyone doing today? It's your professor. Today's lecture's on chapter 10, and that is all about elementary data structures. Data structures. These are all the famous ones, the simple ones that you probably all are very familiar with. So it should be a pretty basic review. And maybe, I don't have it in my notes, but maybe the simplest one, even though we've used it a lot, I should mention, are arrays, right? We use these time and time again, right? Maybe I'll write with square brackets, right? And it's just some set of numbers, right? A collection of numbers. And the interesting aspect about this that I want to point out is, say, accessing them, right? So accessing them, it's by an index, and say if I want the second element, um, it's going to be constant time in order to access this, right? The reason being is because they're stored in memory as one contiguous block. So in memory, these are actually stored, as memory locations. And you have a pointer to this first element here. So when you say you want the second one, it's just doing a little bit of addition to this and saying, well, it's one, then it's the next one over. Take this pointer value and add one to it and you get this. Okay? And similar for the other ones. Now so lookup is really efficient, but you could also, we know that the way that these are allocated, you allocate these arrays, right, in some block of memory. They're contiguous blocks of memory. They have to be one right after another. These memory address, this might be memory address, I don't know, I'll make up some memory addresses, and these aren't even realistic memory addresses. This might be memory address 20. Well, this would be memory address 21. This would be 22, for example, just making up numbers. Okay, it wouldn't be 25 and 30, right? That would not be contiguous, just FYI. So you allocate memory in blocks, right? So if you need to do operations such as, maybe you have your array like this that you've allocated with 3 elements, and let's say you want to add a 4th element, and let's say you want to add it right here. Let's say you want this thing to go to 1, 4, 2, 3. Well, that's a very expensive operation, because what you basically have to do, the naive way to do this, is to allocate an array with um, 4 elements, 2, 3, 4, with 4 elements in it, and add the 4, and then add the other elements back in. So these were from the original array, and then this is the new added element, and you can see how expensive that is, right? So this is where we're going to talk about different ways maybe to solve this if you're sort of in this situation, even though we're usually not, as you'll see. But this is the array, and that's sort of the basic overview of arrays that we probably already all know about, and the book doesn't even talk about them, but just a little side note for you. Okay, so let's go back into actually where the actual book starts with this, which is with stacks. Stacks. Um, last in, first out, right? So this is first out. Okay, so they have data structures, as I've mentioned. Data structures are how you organize. I should maybe have started with this. Data structures help you organize data. Side note, you organize data. And and a part of that organization, I guess you could group it into, is you're going to have operations on that data. So you might have the basic ones, and you might have some of these, all of these. You might have custom ones, right? But these are the basic common ones. You're going to insert data. And they might even, instead of saying insert, you're going to say, you might name it differently, right? But it's all kind of insert. You might delete data. You might update. Oops. and you might read. Oops, fitting everything in here. Read. Okay, read the data. So those are, and then plus other things that you may do, you may not do, whatever. And you may just have a data structure that just inserts, right? That's fine. But it's how you organize data. And again, they're particularly important, and why they're fit in with this algorithms course is because a lot of algorithms, it's how do you organize your data. So we'll talk about ways to do that. Okay, so this is just kind of a little side note on this. A couple little side notes before we even actually start. It's good. So the operations that we'll talk about for stacks are the important ones are push, and this is your insert. They call it push, and pop. Okay, this is your, I guess you'd say delete slash read. It's a read. You read it and then it gets deleted. So delete, read, however you want to think about it. You'll see in a moment. And then there could be other custom ones on here. A lot of ones will have like some operations peek, which is you could just, it's just a read without delete, stuff like that. But we'll focus in on these. This one is easy, and so any other little custom ones that you might see for it. Okay, so a stack, the best way to understand that is through a simple example, and you picture it like a stack of plates and how things are added. So if I had some stack data structure S, and I called push 1, I pushed 1 onto the stack, okay, then it's going to look like this. In your head, this is what it looks like, okay? And then if I call, and then after that, if I call stack.push 2, it's going to look like this, okay, in your head. Notice the 2 is above the 1, okay? It's not the other way. The 2 isn't below the 1, okay? I pushed the 1 on there, it went on there, and then I pushed the 2, and it gets stacked like a stack of plates. You can think of this like a stack of plates. You put one plate on, I put this first plate on, and then I put the second plate on. The second plate goes on top of the first plate, okay? So that's the push operation. Now here's the pop, or the sort of delete slash read. If then, and these are this is the order that I'm doing these instructions, every line of code. That's line 1, line 2. Line 3, if I then call pop, and it'll return some value, so I'll write it like this. And you don't have to provide an argument because it knows what to do. It's going to return, X is going to have the value of 2. And your stack is going to look like this now. Does that make sense? So even though 2 was the last one to get in this order, you went 1 and then 2 got put on, the first thing to come off is the 2, not the 1, okay? That's the key. And then if I call here, we'll do Y, I guess, s.pop, then Y is going to be 1, right? It's going to be 1. So you get the value, right? And it's deleted from the stack. That's why I say it's kind of a get and a delete. And a peek would just be, let's go back to our original state, which was, let's say that this. If I called s.peek, it's going to just, this will be, say, Z, this is return. Z is going to have the value of 2, but the state of the stack will still be 2. It doesn't delete it from the stack. That's another common operation. I don't know what the author decided to call it, or if he even implemented it, but peek or whatever works. Okay. So C++, just this is a good side note. C++ has a stack data structure. Okay, so if you need to use stacks, you can just in C++, and a lot of other languages have them too. So you can just pound include them, and you'll get push and pop and top. They call top, but that's peak, which is what I call peak. You know, they have an empty. You can ask, is this stack empty? So for example, if you called s dot empty, it would return in this case false, right? Because it's not empty. But if it was like this, if the stack looked like this and you called s dot empty, it would be true, right? Okay, not that hard to understand. Stacks are, traditionally implemented via arrays. Implemented via arrays. Okay, so for example, this would represent your stack. Oh, whoops. Remember, it's an array, so it's a fixed size. So I have extra space in this array to hold extra elements, right? That's what these are. I can hold extra elements, so it's a fixed size. It's not growing dynamically. And then you'll have some pointer to this element here. And in this case, the value is 4. Right, this is the index. 1, 2, 3, 4, 5, 6, 7. Okay, so you have a stack. It's a fixed size because it's an array. We'll talk about some famous websites here in a moment, and you'll see why I say that. So s.top, it points to the top of the list, right? So it's going to be this thing pictorially is going to look something like this, right? And then I guess you have a few empty spots up here that you potentially could put stuff in, but the state of it looks like this, right? Your stack of plates, right? Because that's the top. Okay. So now, and again, if you so choose to implement your stack where you reference this as your top, go for it. I really don't care. It's just an indexing thing, right? You can do whatever you want. Okay. So when you call push, then let's call push. And we can write this in a functional way, maybe just to really confuse you. I'll use functional programming or some style instead of object-oriented programming. Let's push 17, and then let's push 3 on here. So this is line 1 and line 2. And I'll just kind of write what the state of the stack will look like after this. Well, the state of the stack is going to look like this. 17, and then I did 3, so that's 3, right? Which is 6 in this case, the value of 6, right? And then if I call pop in this line, and it's going to return some value, it's going to return 3, right? That's the value of x, and then this is of course going to go decrement. Oops, decrement. Right, decrement down there. So that has a value of 5, of course, right? So as you see, it's a very trivial array, indexing, additions and subtractions and things like that. It's trivial. So a few things. I'll get back to talking about famous websites here in a second. So what happens if the stack is empty? So if you have this stack, I'll just draw a stack with a capacity of 3. And what happens if you call stack.pop? I'll go back to the object-oriented notation. Okay. It's going to error, right? And it should error out because there's nothing on the stack. It's going to error out with stack underflow. Right? You're going to get an error message and going to say stack underflow. Okay. Or maybe in your case, you're like, I don't really care, just return -1 because I have all positive integers or something like that. I don't know. The generic way to do this would to throw some sort of an exception and say, hey, it's a stack underflow. What happens in the other case, let's say you have a stack and it's completely full to capacity, and this is the famous website, and you call s dot push, and you want to push another element on there. What's going to happen? Well, in this case, you're going to get a stack. You're going to throw an exception. You're going to get a stack overflow. Right? That's the famous website we all, I'm sure, are familiar with, Stack Overflow. Okay. So what's happened with a Stack Overflow, which I'm sure probably a few of us have gotten those error messages, I'm sure, if you've been programming long enough. It's that your stack is filled to capacity. You don't have any more memory left. Okay. So the next data structure, well, let's see. I'm probably going to talk about, I don't think I really have to go into detail. You can look. The author has implementations for stack. He calls them stack empty. This was just what I would call s.empty or something like that. He has pseudocode for push. He has pseudocode for pop. Okay. All these, as you saw, are just trivial indexes into an array, adding one, subtracting one, blah, 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 things like that. So these are all constant operations. They're just array operations, right? And we know those are constant operations. So the complexity for the stack operations is constant. Okay. Queues are next famous. Okay, these are first in, first out, abbreviated like that. Okay, these are like lines, right? If you get into a line, how these works. And I do the stack vertically. We're going to draw a queue horizontally. So a queue, and they have, again, very similar operations. The author uses enqueue. Okay, this is like his insert. Okay, I'm just going to say push, right? I'm just going to say push. That's what I'll use, enqueue. You can do it, like I said, it's up to you. You use whatever you want to use, and then dequeue. This is like your delete plus read, right? And I'm just going to refer to this as pop, right? Keep things simple, I guess, is what I'm trying to get at. And then, of course, you have the other things. You can do peaks and things like that and ask if it's empty. But again, the way to look at this is you have your queue, and it looks like this on its side. Before, I had, remember, the stack like this. Now I just turn it on its side. And let's do a push or an enqueue. Push under my queue 1. Well, it's going to look like this. And then I'm going to, under my queue, push 2. It's going to look like this. Okay. And then, so 1, you put the 1 on first, and then you put the 2 on. Okay. Now I'm going to dequeue, call some dequeue, or pop. Again, it's going to return something. I don't need an argument. And it's going to return, what's it going to return? It's going to return 1. So the state of this is then going to look like this, right? It's going to look like that. Okay? And then if I call, again, queue.pop, it's going to return 2. And the state of it's going to look like this. Okay? So the way you think about this is like a line, right? So this person gets in line, and then this person gets in line. Okay? And then you're up here, there's someone saying, okay, you can, next person, next. And so what happens? Well, this person, number one, got in line first. So number one comes off, and everyone shuffles up to the front, right? So now two's right waiting. And after one's done, then it says, give me next, and then two comes off, and everyone shuffles on, right? So that's the way to think about it, is plates for stacks and lines for queues. And you can think of them vertically and horizontally, okay? And again, C++ has a stack data structure. And so do other languages, have stacks and queues built into them, push and pop and all this other stuff. So it's just an FYI in case you need to use them in practice. So they're similarly implemented via arrays. And so you get this in here. If we have this queue, or I guess I should use capital Q just to be consistent. So let's see, we need 12 spots for this. I'm going to have a capacity of 12. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. And then I'm going to start filling it from, it's going to be already in this, partially filled. So we're going to start at 7. So it's going to be 15, 6, 9, 8, 4. And then you need 2 indexes. You can fill it from both sides, right? The front and the back. So you need to keep track of both. Okay. So q.head, and in this case it's the 7th element, and then q.tail, which in this case is the last element, 12. Okay. And again, if you want to reference, instead of using, referencing it right here, if you want to use this as your tail reference, go for it. It's just minor indexing, right? It doesn't really matter. I'll just be consistent with what the author has chosen to do. Okay? So, the way this works then is, so again, this is sort of partially filled, so it looks like this if we draw the picture. 15, 6, 9, 8, and 4. And so this is the head. This is where the guy's saying next, and then this is where you add stuff in. This is where people come in through the doors and get into line. Okay? And so we take things off here, and we add things on this side. So that's why you have to have a head and a tail to keep track of everything. You can kind of change in both directions, at both ends, the head and the tail. Okay? So I'm going to do a couple operations, and then we'll look at what the state of it would look like. So if I push 17, and then I push 3, and then if I push 5, what's going to happen is you're adding right to the end of it. So you're going to put a 17, and then this is going to move right to here, right, and then to here. So I can just do this all in one step. 17, 3, 5, and then, oops, let me move this. And then you're going to have your tail to be here. Which is the 3rd element, right? And then if I call pop, it's going to return 15, and of course this then goes away and it moves down here to 8, right? Okay, so that's how it works. It's the sort of circular boundary conditions. You fill it all the way around and take away in a circular fashion. Okay. So these, just like before, you can go look at the authors. He has pseudocode for NQ, which is our push, and DQ, right? Or pop. He has them. They're basic, just like before, array indexing, right? You're just keeping track of indexes. Add one to it, subtract one from it. So they're all just these O of 1 operations. So all of the stacks and queues can be implemented, all those operations can be implemented in constant time. Okay, so just like an array, because they basically are just arrays. So the next one, and this is why I sort of started out briefly like talking about arrays, is because I wanted to compare them to linked lists. And I said, hey, when we started trying to delete stuff kind of in the middle, I said, well, we have ways to deal with that if that's really important to you, and linked list is one of those. Okay, so I should say a linked list. Linked list. And these are pretty, I would say, on interviews for jobs, these are, they pop up for sure. People will see what you know, because it's sort of like a good basic data structure to check your knowledge with. So, so they're similar to, similar to arrays, but not stored in contiguous memory, right? So before we had an array, and we allocated, addresses contiguously, 1, 2, 3. I said it wasn't like this wouldn't be address 5, right? It had to have to be 2, address 2. Whereas linked lists, this could be, in theory, address 5 and 3. That's perfectly fine. These aren't contiguous memory addresses, okay? Those have some benefits and also some downfalls, okay? And in fact, we don't even write it like I just drew that picture. We actually would write it. We're going to start with a singular linked list. Linked list. And this is usually the way you'll see people draw this, is you have, this would be your key. This would be your key. So if you have some structure, what this really is representing, if you'll have some struct with some ID or key, we'll just say ID, I guess. In this case, it would be 1. And then you'll have some data here that will be whatever. Some data, age, height, blah, 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 that you're interested in, right? And then you're going to also, in this struct for a linked list, you're going to have a pointer to the next node. Next node, okay? Just FYI. But we'll look at it pictorially first and what is in your head. So you have to have a little bit of understanding of what pointers are, or references and things like that. So this is your key. And then this right here, this box right here represents the next pointer. So you're going to have a pointer, right, which tells you, a pointer is just an address. It's going to point to something. It points to another node. Okay, so that's what we represent by the pointer, and that's why we're saying this box is the next, and it points to and oops, I'll actually represent it a little bit more rigorously. We'll do 2 here, right? It points to this node right here, to this box is what we're representing. It says, hey, this is the next one, and then this one has a little pointer right here that points to the next box. Okay. And then this one is going to point to null. That signifies or flags that there's no the end of the list. Okay. And so they call this the tail node. This is the tail node. Right? This is the next pointers. Both of these. Right? the thing that gets you to the next node. And then just like arrays, we had arrays, 2, 3, which were represented like this. An array, you're actually given only a pointer to this node, the 1. You're given a pointer to this, and only this. And then you figure out, based upon some pointer arithmetic, how to get to 2 and 3. Okay? So similar to this is the head. You're only given a pointer, and actually let me draw it like this, to the head of the linked list. Okay? So if I give this thing is out in memory somewhere. Notice these are not contiguous memory locations, right? This could be memory location 5, and this could be memory location 10. This could be 5, and that could be 10, and that could be 20. I don't know. I'm making numbers up. Okay? So I'm given the memory location 5. So I know where to go in memory to get that. I say, hey, go to memory location 5, and that's going to take me to this. So I can get the data there if I need it. And then if I want to get the other data, I just call next on this. And I'm going to go over here. And that's going to give me, this one holds the address of where I need to go find this one. I can get the data there. And then if I want to get the other data, well, this one holds data to, tells me where to go to get the next thing. So I just follow this and it'll take me over here. Now I can get that. So you see it's linked. But I'm getting addresses. They're storing the address of where to go. This would store the address 10. This would store the address 20, right, in this example. Because this 1 says, hey, all right, I want to go to the next one. Where do I go? Go to address 10. Where do I go here? I'm at this one. Where do I go? Go to address 20, if you want, et cetera, et cetera. And then I come here and I say, go to address no. Oh, I'm at the end of the list. Okay, you're done. Okay, so there's different types of linked lists. We just talked about singly linked list. These are pretty much just textbook ones that you do. I believe that C++, I'm almost positive C++, actually no, I know for sure, they use doubly linked list. Okay, we'll talk about these briefly. It's pretty trivial. And then there's also circular linked lists. Okay, so basically all this is it loops back on itself. So instead of it pointing to null, you're going to point back to the head. So you just can go, you just go through around and around and around. There's no checking for nulls and things like that. And then you also have sorted or unsorted linked lists, right? So you might be sorted by keys. Or not sorted by keys, right? That might be important to you to have all the keys sorted so that when you traverse, this might be like 1, 2, 3, that would be sorted, or it might have it like 3, 2, that would be unsorted by key, okay? So double linked list, as I said, that's the common way that these are usually implemented, and those are just the fact that you have an extra link in there. So before we had it look, I'm not going to draw the extra stuff in there, it's kind of a pain. We had something that looks like this. This was what we had before. And now, so I said if you were at this first node, node 1, it gave you a pointer to next. But in fact, now you have 2 pointers. You have a pointer back in on itself. So let's say I'm at pointer, let's go to 2. That's a good one. Let's say I'm at 2. I only know how to get to 3. I don't know how to get to 1. If I wanted to get to 1, I'd have to traverse, or I have to go back to the head, right? But if I add extra links in, I have more degrees of freedom. Now if I'm at node 2, I can get to node 3. I could do that before, but I could also now get back to node 1 where I came from, okay? And you have complete freedom in this. If you, for whatever reason, for your data structure, maybe you're referencing the tail a lot. So maybe you always want to store an extra, every pointer you want to also store an extra bit of memory in order to reference a pointer all the way to the tail or always to the head. You could do that too. So you don't have to traverse the list. You can just, if you're at some node, if some condition happens, just go to the tail. Well, I can get to it really fast. So that's how you can sort of augment this data structure and get to fit your needs. But this is a common one. And there's good reason for it. Basically, it's because you can do deletes really fast. That's why, for a little bit of extra memory. And of course, C++, just like stacks and queues, they have lists. They call it, or it's include. They just call it list. Okay, and other programming languages will have them. And then it's a doubly linked list. And you can look at the operations. It's push back, pop front, pop back, blah, 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 blah. Okay. So that's the idea of them. Let's look at some of the operations. Let's see if I talk about delete. I think I talk about delete. Yes, I do. Okay. So let's talk about. Oh, I talk about inserting. I don't think. Yeah, I do inserting. I do deleting. And I do lookup. Okay, good. So he calls this searching. You could also consider this lookup. So just like an array where you'd say, give me node 1, that's the operation that I'm comparing to. Give me node or index 1, index 2, the third element, the fourth element, blah, blah, blah. He calls it search. I would call it lookup or getting a value or something like that, okay? So he'll say list search is what you'll see for him. But again, I want to compare it to this operation because that's essentially what's happening. You're trying to get a value. Searching a value in a linked list is what it is, amounts to. Okay, so if I have some lists and I'll write it like this, I'll try to remember to use squigglies or curly brackets. If I have a list that looks like this, what's going to happen then is this is going to be represented in memory. Okay. And again, maybe I guess I was trying to emphasize the fact that this is sort of an unordered list, but I guess maybe I probably should change this notation so it looks a little bit, it matches this. So maybe I'll change this in my notes because that's probably a little bit confusing. I'll write it like this. Okay, I have to change that. All right, so perfect, and then 1. Okay, so I have a reference here to the head. I know the address of this node. Okay, I know how to get to number 9. So if I call, and again, I'm going to just use this notation, list of 4. This isn't saying give me the fourth element. This is saying give me the element with key 4. You can see this is actually the third element or the third index in this, but I'm saying I'm just sort of to draw the analogy of the array notation, right? In this case, I'd say give me the third element if it was actually represented as an array, right? And it would go 1, 2, 3, and so it would return 4, right? But trying to draw the analogy, okay? So I'll use this notation, but it's really saying search, list.search for the key 4. So what's going to happen to search for this? You're going to go through one by one. You're going to enter in here because I know how to get here. I use that reference. I'm going to say, is that equal to 4? No. And I'm going to call next. And I'm going to use this chain to get over here. And I'm going to say, is this equal to 4? No. So then I'm going to go and use call next. And then this chain is going to take me over here. And I'm going to say, is this equal to 4? Yes, it is. Sweet. So it's going to return let's say this had an address of 20. Again, I know these are not normal addresses, but I'm just trying to make these numbers simple. It's going to return the address 20. Okay. You could implement this if you just wanted maybe the data in there. You could have it return the data that's in there, or you could or whatnot. But returning the address, you can then dereference it, right, and get the data in there. So the easiest way to think about this is it returns a pointer to this. So I know we're at in memory to get to this thing is it. So that's gonna return the address 20. So I can simply just dereference that address and boom, I've got it. Okay, I have a pointer there. Okay, so you can already see a difference here. I hope in trying to the lookup. The lookup is that so best case is going to be it's the first element, right? First element. What if let's take a side note. What if I asked for list of 7, element 7? It's going to return null basically, right? It's a pointer, null pointer, which means nothing. It didn't find it, right? It's going to go all the way through this, and it's going to then call next, and it's going to say, hey, it's null, and you're going to say, okay, let's return null. It's not there, right? So if it's the first element, if I was looking for the key 9, then I've gotten it, right? So that's going to be the best case. What is the worst case? Is going to be n, right? That is last element or the null, right? It doesn't find it. So if I have to then, if I look for element 7 or element 1, or any so element 1 or any element that's not in the list. For example, 7. Why do I use that example? Because that's the one I just used. So I'm looking for 1. It's going to traverse 1. This is a terrible color. This element, this element, this element, this element. N elements. It's going to traverse all n elements, right? So that's a big observation on this, comparing arrays to linked lists. That's the first observation. Is that your lookup by some, this is just an example. Example is this is worst case order n, and this is worst case constant. Okay, so that's the first major observation. And then it'll be somewhere in between this, right? Yeah, how often you get the best case theta 1, right? Not very often. And the average is going to be, you're in constant time. That's a pretty amazing thing that you can accomplish, okay? Versus linear time. And this is really the one observation of why linked lists are sort of not used as much as arrays, okay? But hold on, I have more to say about this. What about inserting into a list? And then we'll think about inserting into an array. Okay. So inserting. And we're going to, for the moment, concern inserting into front. We can, I'll probably mention inserting in the middle, inserting in the back, but in the front, and the reason why we chose the front is because it really emphasizes a comparison between arrays and linked lists, okay? That's why we chose it. It really demonstrates the power of linked list if you have a situation like this. Okay, so inserting, if I have, and I'm going to use a double E. And I have a pointer here to head. So let's insert 25. Insert 25 into this. What's going to happen? It's pretty easy, right? All I have to do is I know how to get there. So I go, let me erase this to give me some space. I'm inserting 25. I'm inserting 25. So I go here. I go, okay, I get this. Let's just add another chain. Add a couple chains. Add the 25. And then move my head over here. Okay? It's simple messing with pointers. All you're doing is flipping pointers around. Okay? You're changing what pointers are referencing to. Okay? Your head, next, previous. You're changing a few pointers. 3 pointers to be exact that are getting flipped, messed with. Okay? That happens in constant time. Wow, that's cool. So, and if you have a pointer to the, you can insert at the end pretty easily too. It's the exact same thing. You just need to also hold a pointer to the tail of the list, right? If you had a pointer to the tail, and that's pretty trivial to do. So you could do it at the end, at the front. I chose the front without loss of generality. You could also pretty easily. This is more side note. Pretty easily. And I want you to compare to, think about arrays trying to do something like this. Let's go back to the beginning. Insert something in towards the middle, right? Let's insert something between 16 and 4. Let's put something right here. Well, that again, yeah, you have to search maybe. If you know where 16 and 4 are at, if you have references directly to here, it's not a big deal. If not, you might have to search for it, right? You might have to search for it. But it's pretty easy, and it's just simple. This is all the same. This is all the same. This is all the same. You come in here, and let's put 25 in here. And you just stitch. Again, you're stitching a few pointers together. Right? You didn't have to mess with this. You didn't have to mess with this or anything else that might be on this side. You just had to mess with a few things here. And in fact, you just messed with this pointer and this pointer. 4 pointers in this case. You just had to restitch together. Nothing fancy. It was just put this here and put this here and reference this here and reference that here. Right? It was that simple. You didn't have to mess with the head or anything like that. Okay? So you can see, versus the array where I told you if you had something similar to that, you saw what a nightmare that could be. If you want to put 25 here, oh gosh, reallocate an entire new array, copy everything into it, insert the value over what an absolute, I mean, think what a pain that is. Okay, so you're already seeing some beauty in inserting. Okay, so it's this, for this case in the front, it'll be constant for that case. Okay, so let's summarize. List versus array. Okay, theta n. This is for your get, right? Like list of 4 or array of 3 or something like that, right? Versus constant. To get an element, to look up an element for an array, it's all contiguous memory. It's just element 1, element 2, element 3. It's simple. It's constant. For a list, at the worst case, you're going to have to traverse that entire list because you don't know. Is this the key? Is this the key? Is this the key? Is this the key? Oh, that's the key. You might have to go to the end, or it might not be there. To add or insert, and we just use the case of front, but you saw how, hey, look, if you have it, it's easy to do to the back. It's also pretty easy, especially if you have a reference to where you're trying to insert it. Very easy to stitch a new element in there, okay? But we'll just consider the front. Constant versus this is n. Why? Well, you have to copy. You want to add a 4th element to this. You have to copy. No, Okay, right, you have to allocate a new array, and copy, we'll add it to the front. We'll add 4 to the front, just like, well, I want to add it like be 4, 1, 2, 3. So you have to allocate an array with 4 elements, okay? That's not going to take too much time. Then you have to insert one element. That's not going to take too much time. The expensive part then is then copying over all these n elements. 1, 2, 3. There's n elements, so it's a theta of n to do that copy. It's a for loop, right? To fill out all these. That's the expensive part, not the allocation and not the inserting of the one extra element at the front, okay? So look at this. They're kind of, as you see, opposites of each other, right? They're opposites of each other. So when should you use an array? When should you use a list? Use arrays when when getting values, reading values, looking up is really important to you. Use a list when inserting values, particularly at the front or the back or in the middle, is really important to you. Because, and again, and I should say this, reading values for arrays is really important, and you may not do too many in, having to expand their array. You might have to not have to do that often. Versus a list where you might have to be inserting elements in the middle a lot, or at the front, or at the back a lot, and you're very rarely actually trying to get a value, right? That's the balance. The question I have for you then is, how often are you inserting values at the front or the middle of an array? And for that matter, maybe even the back. Versus how often are you looking up things? A lot of times, right? Usually we know have some sort of information about how much data we need to store, and it's just looking up, right? So it's not that big of a deal. So linked lists in practice aren't used that often. There's one caveat to that, in that I know many of you are familiar with certain like dynamic arrays. Oops. This is C++, but more generally we call it dynamic arrays. And these things automatically expand, right? You'll start filling it up 1, 2, 3, and then you want to add another element to it. Let's say I want to add 4 to the end. Well, it'll just automatically expand, and you're allowed to add 4. Okay. What about? I'm not talking about dynamic arrays right now. Okay. So I'm saying if you have this case, is what this assumption is. And I said, hey, linked lists aren't really used because usually we're looking things up. Let me even make it even better for you why you probably should avoid linked lists in general practice. Right? You don't really need them in practice. Sometimes they're very good things. Okay, so I'm not trying to indicate don't ever use them. How often are you adding things to the front? How often are you adding them to the middle? Very rarely. If anything, you want to add things to the back of the array, right? And I'm here to tell you that there are very easy ways to add things to the back of arrays, and there are these dynamic arrays. Dynamic arrays are vectors in C++, and every language has their own form of this. Okay, we have ways to handle adding things to the end of an array. Okay, and still in constant time, blah blah. This is a caveat. I have to talk more about this, but you're not going to kill your runtime. Okay, in an efficient way, we can do this. So not only can we look up things in constant time, we can also add things to the back of an array using dynamic arrays in a very efficient way. And again, I'm doing in quotes theta of 1 constant time, and we need to talk more about that, but it's very efficient, trust me. So unless you're really adding things in a weird way to the middle of an array, that might be an argument why you want to use a linked list. Maybe the way you traverse things is naturally you need to go here, and then you need to go here, and then you need to go here, and then you go here. Like file structures, right? That's pretty natural. You go to this folder, and then you go to this folder, right? You can use linked lists and things like that. So I'm not trying to deter you from using linked lists. I'm just telling you that your first thought process, if you need because arrays, gosh, we use them all over the place. Your first thought should be to use an array over a linked list, and that is supported by not just me. The creator C++, for example, he very much so is sort of has said similar things, that you should be very weary about using linked lists in practice, and you should prefer these dynamic arrays. He says dynamic arrays. Okay, he's getting at the same point as what I'm saying with using arrays. Vectors. Okay, he is C++ vectors, which are dynamic arrays. So prefer vectors over linked list, or the linked list data structure. Okay, that's the general take home and my personal advice to you. Okay, so the next thing is going to be deleting from a linked list, and that's pretty easy too. That's why we want to use a doubly linked list. Okay, so deleting, let's say you have 25, 9, 16, 4, 1, null. This is my head of this, and I want to delete the fourth key. Okay, I want to delete the fourth key, so I'm going to delete this. Remove it. Easy, right? Now again, if I have a pointer to this, the element I'm trying to delete, and I can go straight to it, this is really trivial. If I don't, I may have to search for it, which takes order n at worst case, right? But let's say, okay, so you'd either have to traverse it and get a reference to it, or you have a pointer to it. Let's just start saying, make things simple and say I have a pointer to it. So now I'm here. If I have a pointer here, I know, and this is why the previous's are nice, I know what needs to be linked together. I need to link the 16 and the 1 together. That's why the next and previous are, hence a double linked list is super nice for deleting. So I just need to stitch this together. So I literally just need to do, I'll even show you kind of how this would work. You can just do something like that, right? And you'd probably, if you allocated memory, you'd want to make sure you deleted that memory location. But that's essentially all that's happening. You're just linking some, putting some links in there, okay? It was that simple, okay? So theta 1, if you know the pointer, right? Pointer. If not, right, you're going to have to search for it, which is worst case linear, right? Search for it or look up, right? I said the look up, which is like, look for key. What did I just delete? 4? Look for key 4. Look for key 4. Okay? I have to be careful because when you say, I don't like using this notation search, because when I say search an array, that has a different meaning. It'd be like you're searching for the key 4 in there versus look up, which is just like look up index 4. Boom. So that's why I say I have to be careful with, I don't like to use the word search. I like to use the word lookup, because you're saying give me, element, the element with value 4, or in the array it's the index with value 4, versus search in an array, which we know search in an array is also going to be linear because you might have to go through the entire list. But that's a separate topic for another day. Binary trees, we've talked a little bit about those. I guess why not? I'll mention this too. We've talked about this when we talked about trees, but we'll go ahead and review, because this is where the author starts introducing them. And again, it's a tree with most 2 children at most, right? That's the key. It doesn't have to have 2. And I'll draw it like this. I just making something up. So at most, again, you can see this one only has 1. This one has none, right? This one happens. This one has 2. At most 2 children. At most children. Okay, C++ does not have trees. All these other data structures I've talked about, I said, hey, C++ has them. Why doesn't C++ have trees? Well, the general consensus is the fact that it would be hard to efficiently represent a tree data structure to suit everyone's needs. Okay, so that doesn't mean people haven't implemented tree data structures in C++. In fact, boost.graph, graphs are trees, so this is a possible option, or you can go find some other code out there that will do trees for you, but they don't have them built into the language by default because they can't be implemented efficiently for everyone's to suit everyone's needs. We saw with like a binary heap, which was like a binary, it was a binary tree, a special form of it. We used arrays, right, to implement them. You could also use linked lists to represent a tree, right? These are just, remember I told you, you shouldn't technically draw these arrows, but people do because people think of these a lot of times as the lengths, the pointers, right? So you have a pointer in your data structure to your left child, and to your right child, right? So if I give you a pointer to the head, which we'll call root, I'm going to go here, and I want to go left child. Okay, and then I want to go to the right child. Boom. And I want to go to left child. Null. Okay, great. That's a leaf node. That's how this works. So it's just links in a chain. Okay, your data structure is going to have a pointer to the left child and a pointer to the right child. Okay, if it's leaf nodes, those are going to be null. Okay, your head is going to point towards the root node. Your root node. It's that simple. Okay. Here's kind of a fun little side note to end the chapter is, I guess they are rooted trees, which are arbitrary number of children. Not just two, not necessarily just two, but let's say you can have up to, just as an example, k children. Okay, so for example, I'll draw I guess I'll just be consistent with what I have in my notes. Again, you see I'm drawing these arrows. It's just, I'm used to it because these are thought of as links. So you basically would have, if you're like, well, let's just make this assumption. We're going to have an arbitrary number of children. I'm going to say, well, let's just assume I can only have three children. Up to, so in this case, 3 children, up to 3 children, or k children. Well, you're going to have, in this case, a pointer to the left child, the middle child, and the right child, right? And this is not general, to waste of memory. The trick to solve this, and this is why I kind of like this, is you only need 2 things. You need to represent an arbitrary number of children. You need a pointer to the left child and a pointer to its siblings. Okay. So this node needs a pointer. You only need a pointer to this. Let me do a different color. You need a pointer here. And then you need, and this one doesn't have any interesting pointers, but this one has an interesting pointer and a pointer here. Right? So it's, and then this one, which is this one now here, is going to have a pointer here, left, and then a pointer to all of its siblings, etc., etc., etc. So you have at most 2 pointers, right, in each data structure. Some of them are null, some of them aren't. But instead of saying, oh, let's assume I only have 3, or which isn't general, or let's assume I have, okay, let's make a big number because I might have a big tree. Let's assume I have 10, right? Not general. So you just need left child and then to all the siblings. And you can just follow the links, right? I can go, let's try a different color. I can go here, and I go here, and I go here, and I go here. You can see how I get to it versus, well, if I want to get there, I could go here and here, right? Now I have to go toot, 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 toot. Okay. That concludes this chapter. Thanks.